I'm going to focus my 30-minute talk or so on this particular topic of dealing with how are we making progress on resolving the up-dip portion of rupture for large earthquakes. The classic idea, this little cartoon here is kind of the conventional thinking, is that the plate boundary thrust faults, the megathrust faults in subduction zones, have a region of strong coupling that produces large earthquakes that is from about 15 to 40 kilometers deep, 45 kilometers. And the very shallow toe of that is an area that is much weaker and doesn't accumulate strain and doesn't tend to participate in large earthquakes, and is defined in between large earthquakes by the existence of an up-dip limit to seismicity, or an aseismic front. And that perspective has been challenged over time by the occurrence of some events that do actually rupture all the way to the trench. And it's changed our ideas that the very shallow sediment and fluid-rich toe of the wedge is in fact capable of participating in large earthquake ruptures. So to talk about this topic, I'm going to outline some of the advances from joint analysis, from seismic, geodetic, tsunami analysis for large earthquakes that demonstrate that you can have rupture to the trench. That'll be very familiar to most of you. And then I'm going to look a little bit at new aspects of seismology that might help us to also confirm this behavior, in particularly with the prospect of being applied to older earthquakes that preceded the availability of particularly good seismic, geodetic, and tsunami data. So I'll try to get to that. Well, why do we care? Clearly, the shallow part of the megathrust, the conventional idea that it's stably sliding, it's weak sediments that cannot accumulate strain, has been challenged by events like Tohoku, and this other event is a Mentawai off of Sumatra in 2010. Earthquakes that have a lot of slip all the way to the trench, at least in some models that I tend to trust are a fairly reasonable representation of slip. There is significant slip in the upper 10 or 15 kilometers of the plate boundary contact. And that is in the region that background seismicity would largely have had an aseismic behavior in that region. And people would have anticipated it was not going to be able to participate in a large rupture. So how do we study this? Everybody here knows the answers, that if you can use on-land geodetic data, study static deformations. We use this to constrain coupling. We use it to constrain coseismic slip. But to be honest, it's not very high resolution about the shallow slip because you're far from the stations, particularly if you have a wide megathrust boundary. And if you're just using on-land geodetic statics, you don't really have very good resolution. That's unfortunate. If you can have offshore geodesy, then you can do much better. And that played a huge role, of course, with Tohoku. And I'll mention a little bit about that later. We only have that in limited places, though, still. And over the last 10 years, where there have been a lot of big earthquakes, I'd say the greater role has been played by tsunami recording and modeling the tsunamis, because the tsunami are slow-moving waves that are particularly sensitive to the location of slip. So by the improvements that I'll show in terms of being able to predict the waveforms quantitatively, we've really advanced our ability to constrain for a large earthquake, whether it slipped all the way to the trench through this aseismic front or not. Seismic wave data can contribute to this problem, but there's no question as you get very shallow, the resolution from seismology is diminished. Mainly the destructive interference with the depth phases makes it difficult to nail down the slip. But if you put the seismic data joint with tsunami data or joint with geodetic, particularly offshore geodetic data, or together all three types of data, you can really improve the resolution. I'll show an example or two of that. And then finally, I'm going to emphasize a purely seismological approach that we can look kind of retrospectively at older events with, which is exploiting the generation of reverberations in the water that are excited when you have slip all the way to the deep water near the trench. Well, I've been interested in this problem for a long time. This is a slide that goes back 20 years or so that from Susan Billick's work when she was in her thesis, doing her thesis at Santa Cruz. And it displays one attribute of small earthquakes at shallow depth. So these are, as a function of depth from the trench downward, the duration of earthquakes. And these earthquakes have all been scaled to be equivalent to a moment magnitude of 6. And what you see is that there's sort of a hook trend with at the shallowest depth end, the earthquake duration for these scaled equivalent seismic moment events can be unusually long. And this early on suggested that as you go from the main zone, from 15 to 45 kilometers deep, where you have most big earthquake slip, you come up into the upper 15 kilometers, then the rupture duration is longer for a given size earthquake. So a typical magnitude 6 would take 4 seconds to rupture, and here we had events that were taking scaled durations of 10 to 15 seconds. Now this is connected to the occurrence and the observation of tsunami earthquakes, which are occurring in this upper shallowest part of the fault. And they're highlighted in each of these regions by the labeled numbers. You'll recognize them. So the 1946 Aleutians earthquake, the 1992 Nicaragua earthquake in Middle America, some large events along Peru that were tsunamigenic, particularly tsunamigenic, 1896 Sanrikuoki along Honshu. But those giant events are accompanied by smaller earthquakes that also show unusually long durations when they're rupturing the shallowest part. And this suggests that there is some difference in the friction, difference in the energy release as a function of time, the speed of the rupture or the stress drop of the sources when they're in the shallowest part of the fault. And so it sort of makes sense that these are, in fact, rupturing close to the trench, but they are a little bit different. And that tells us that the shallow domain has some attribute that's not perfectly well characterized, but it doesn't go all the way into the slip velocity strengthening type of environment where you don't have those earthquakes at all. They actually do occur at those shallow depths, and they tend to be unusual in their durations. Now, in the last 12 or 15 years, I worked on a lot of earthquakes over time with my graduate students. And of the 120 or so earthquakes around the world that were interplate thrusts, the events on this megathrust boundary, about 10% of them seem to have ruptured the trench, but maybe 90% of them did not. And some are very well constrained, like this event, 2012 Nagoya, Costa Rica earthquake, which has been studied by many folks here. The availability of seismic and geodetic data on the Nagoya Peninsula extending out to within 60 kilometers of the trench really allowed you to resolve the slip. It did not rupture to the trench, and that's true of most of the events. Okay, so I'd say it is about 90% of them. There's not any clear indication of rupture of the trench, and we don't always have this level of resolution. I think it's probably the case that this is the best resolved slip distribution that we have. So because the slip is all under the Nagoya Peninsula where we have a lot of data. Now there are slow slip events. There's interesting up-dip phenomena, and it's a question of whether there could be slip at shallower depth is still being addressed, but it looks like it's mostly with episodic slow slip events, the shallower part of the fault is failing. Okay, but that's like 90% of the events. Those are not the ones I want to talk about because we're pretty confident they didn't rupture to the trench. The more interesting 10% are those that do, and I'll show a few examples, one of which is this event off Sumatra in 2010, the Mentawai earthquake. It was off the Pagai Islands, and it happened to rupture up-dip of an earlier very large earthquake in 2007, 8.4, and it's 7.9 aftershock. And those are in the blue and orange color background. And when this earthquake happened, it produced a very large tsunami on the Pagai Islands, and it's not a very big event, a 7.8. And so we studied it with standard seismological finite fault inversions. Other people in the room worked on it as well. And this is an example of a seismic model. It shows that maybe slip does extend to near the trench. Okay? And that is interesting. It's not as well constrained with just the seismic data, but there's at least evidence that it did slip with fairly large amount of slip. But because the seismic resolution is not very good for very shallow slip, there was uncertainty in such a model. Fortunately, in this case, there are additional data sets. For example, there's tsunami observations at tide gauges, shown here on the left. Each one of the red dots is either a tide gauge or no, they're ocean bottom pressure sensors. The white dots are tide gauges. There's not a lot, but there are some high-quality data. And along the islands, you had the sugar array. So you had the high-rate GPS data being collected there initially by Caltech and then by Singapore. So we could put those data together with the seismic data and do a joint inversion. And many in this room have developed these methods and know as much or more about this than I do. This is an example where the top are showing you can fit the tsunami recordings at these tide gauges and ocean bottom pressure sensors, one of which is right at the trench, as well as the high-rate GPS on the lower left, the time varying. These are 1 second solutions. And because you're in a very complicated environment, we're using simple models. We don't fit all the wiggles, which are little surface waves from pulses of slip. And you can fit teleseismic body waves in a subset as shown here. You can invert them jointly, and when you do that, you get a model which really supports the idea pretty robustly that the slip extended to near the trench for this event. And it was, in fact, more concentrated than the seismic model, because the seismic models have limited resolution. And here, the GPS plays a huge role. So we have good fit to the primary GPS on the Pagaya Islands. And it forces you to concentrate slip at the trench with enough moment to match the seismics, but far enough away from the islands to match the amplitude of the geodetic data. So this is a case where it really did happen, and it's up to 15 meters of slip failing on its own. It was not participating in a big rupture and being driven into failure mode, as is often invoked for earthquakes. It just ruptured on its own. So an example where this updip region is capable of storing up strain and releasing it in this shallowest part, which is often deemed to be a seismic. And of course, this was tsunamigenic. It produced a tsunami about 15 or 16 meters on one of the islands off of the Pagaya Islands. And there was a lot of loss of life from the smaller tsunami that swept into the main coastal area. Okay, that was a small event, and it was one that just ruptured in isolation up near the trench. An example of rupture across the fault is 2010 Chile, and this is now about a 500-kilometer long rupture zone. It's re-rupturing the 1928. It's rupturing through the Darwin Gap to some extent, and actually down overlapping a little bit of the northernmost part of the 1960 rupture. Now, along Chile, of course, it's amazing to think that this is just 8 years ago. The data availability has changed tremendously in Chile in terms of stations. It was not great at that time. There were a few high-rate GPS stations operating with 1 second sampling. Those are indicated in the plot A. There are a few tsunami sensors of the NOAA buoys offshore. There were a couple of INSAR passages, and there's a good teleseismic data set. And so we tried to study these collection of observations and put them together for this much bigger rupture. And that's a more challenging thing than with a very compact rupture like the Mentawai event. And the standard in the community is to assess how to do a joint inversion by evaluating how well you could do with the individual data sets and trying to find their complementary capabilities and do weighting and merging of the data so that you kind of optimally recover the structure. And you do that by putting in the input models, one of these peculiar, it's a true kinematic model. There's a rupture expansion. It's got an alternating slip patch distribution, and that you construct the synthetic GPS or tsunami or seismic or INSAR or ground motion data sets that correspond to what your actual sampling is. You invert them separately and see how well you can recover individually the input model, or by putting the data together in a sensible fashion, can you do better? And of course, you can do better. And this is, the community's really validated these approaches, though it's not cookie cutter at this point. And for example, the high rate GPS, because they were very localized and near the center of the rupture, they do pretty well at getting the near epicentral data. Teleseismic data, you guys can go ahead and laugh. It's not that great, I agree. The INSAR data is wonderful under land, it's awful offshore. The tsunami is wonderful offshore, it's awful under land. So clearly what you want to do is exploit those complementary sensitivities, and then a good joint inversion can do well, as has been demonstrated by many of you with other data sets and for this event as well. Now, the advances in modeling of each of these kind of distinct signals is very profound, but perhaps the most gain has come from the improvement in modeling the tsunami. We can certainly fit the geodetic motions, the seismic motions, account for most of the smooth INSAR deformations supplemented by the many campaign GPS that are available, and do a joint inversion. But the tsunami plays a really big role because it's very sensitive to the placement of slip because of the low velocities. And in order to match the arrival times at the offshore DART stations, you have to put slip in the right place. But you also have to calculate the propagation of the tsunami accurately. Been significant advances in our ability to do that, to correct for things like salinity gradients in the ocean, to account for elasticity of the medium below the ocean, which had been ignored. And when you do that, you can come up with a joint inversion that has, I think, a little bit more credibility than the other inversions of separate data sets for this event, because we have this nice complementarity of the sensitivity of the different data. And this is an example of the model that we got. This is Han Yue, who was a graduate student a couple years ago, and it suggests that, yeah, there is non-uniform slip. That's not a surprise, but in a couple of patches of this, 15 to 20 meters of slip is extending all the way up to very shallow depth. Okay? And that would be the red areas in the north and the south. And that was in contrast. I won't show some of the other models, but many of them had no slip extending to the trench and concentrated the slip at greater depth. There is, if you look, the relative comparison of where the aftershocks are and where the focal mechanisms and distribution of microseismicity are after the event. The areas with really big slip tend to not have many aftershocks, so you can't rely on aftershocks alone to say whether rupture extended through the trench or not. You really have to have kind of independent information from particularly the tsunami modeling to try and to trust this. There is some indication on the left that the regions where slip, we would contend in this particular model that extended the trench are the areas where you have concentrations of outer rise normal faulting. And I'll come back to that at the end. When you rupture to the trench, I think you have a greater tendency to activate intraplate faulting seaward of the areas where slip goes to the trench, and this is supportive of that. Now, these are just models, and you'd like some confirmation, so there has fortunately been some repeat reflection work on transects. The red track at the top goes right through the slip patch from Han's model that extends to the trench, and they see that the toe of the fault, or the toe of the wedge, actually did move all the way out to the trench, and that in detail, the fit from the model we have rupturing the trench fits the data far better than those which are a dashed line that don't fit, that don't have slip going to the trench. So you'd like to have more confirmation like this, but you feel pretty good when they publish a paper independently and it at least supports that basic contention. Let me do one more example of such events, Tohoku, because it's got the best data set and it also has some of the most important problems. To the north, we had the great 1896 tsunami earthquake that Hiro Kanamori had documented so well. And that was a shallow, near trench rupture as best we can determine. It's been studied, Kenji Sataki and others have analyzed the tsunami. Looks like it did rupture to the trench. It's a very big event and produced up to 40 meters of run-up on the Sanriku coast here. And then you have 2011 rupturing and spanning the area that had been the location of prior activity for the last couple of centuries, going well beyond those. Now, early seismic models pretty consistently suggested that rupture could extend to the trench. So these are just a handful of them. I wrote a review paper, but there's like a total of 80 models for this earthquake. They don't all agree. But a common attribute of the seismic models was that they liked strong slip near the trench in various solutions of teleseismic signals. But the seismic data is not all that well resolved near the trench, so you'd really like more than just that. But for what it's worth, the seismologist got it pretty right as far as I'm concerned. The geodesists, using just on-land observations and a typical assumption that you make the slip go to zero when you can't resolve whether it's 0 or 100 meters, a reasonable thing to do, pinched out the slip. Almost all of the geodetic solutions from on-land static motions kind of had very little slip out toward the trench, and the concentration of slip down dip. And it's led to some conflict of, some people saying the seismology's got it wrong because it doesn't have any resolution, you can't trust it, and some people saying the GPS is not that good far offshore, so you can't trust it. So you have to do better than just the static GPS. I think we would all agree. With Hanyue, I worked on analyzing the high-rate GPS, which was great because that had both the seismic attributes and the geodetic attributes for the many stations on Honshu. And in those models, we got a lot of slip down where geodetically, definitely there's a lot of slip, but we also got slip going to the trench, mainly from the kinematic information from the high-rate GPS solution. So the seismic part of that, which is P wave, S wave, Rayleigh, love wave in the near field. And that just gives you more resolution than the static because the timing information is there. When you add in the offshore GPS acoustic, and there was also some OBP data available, the second generation of geodetic models got much more slip out near the trench and start to converge. So this is without the offshore data. With the offshore data, the slip area contracted tremendously, larger slip further offshore. And I think most people accept that within static solutions, these are very good models, and I saw them several times today. But the key data is still tsunami, in my opinion, because I think you could reconcile the seismic and geodetic data without so much slip at the trench as the purely seismic models had inferred. But along Japan, all these little white dots offshore are regional ocean bottom pressure sensors or GPS buoys that give you good recording of the passage of local tsunami. So we can use that data. And I'm going to show it because it's just so impressive to me that, if you take a kinematic model like this is from a seismic model, just prescribed time-dependent rupture, which is producing a time-dependent deformation of the seafloor, which is producing, without assuming that these are exactly equal, you're getting the time-dependent disturbance of the sea surface. Once you have this and then you relax it with the gravity wave, you get an expanding tsunami. Right? So this type of modeling has gotten very advanced now, right? And as long as you have good bathymetry and you have good clean data as is provided by these offshore buoys, they're not in the harbors. We have a lot of harbor resonance in the shallowest water. It's very difficult to model often. We can make tsunami simulations that I think they fit seismogram-like shapes as well as seismologists do, except look at the time scale. This is hours, right? It's like 3-hour window. So they are just fitting extremely well. This is from starting with the seismic model and perturbing it a bit to try and fit the data. And it's a demonstration of existence. It's not a unique model. It's very hard to formally determine uncertainties, and I'm not a Bayesian person. But I am impressed when you fit the waveforms with a self-consistent model. And so you can fit the data exceedingly well. You can also take the far field, the tsunami going out through the Pacific, recorded at NOAA dart buoys all around the Pacific, and fit those extremely well as in addition. And this was done a couple of years ago well, we started this a couple years ago. And so we do have to allow for some time shifts. We haven't put in all the effects of the solid Earth, but those are mostly static time shifts. There's very little dispersion in the waveform. So you can fit the tsunamis extremely well. And so the tsunami modeling community has done a great job in the past 15 years at improving the ability to reproduce the details of those waveforms. And because the wave is moving so slowly, it's very sensitive to the distribution slip at the source. In addition, and even more impressive technically, is the ability of the new codes to calculate realistic run-up onto very irregular coastlines. You can't do everything. A lot of the observations are kind of made after the fact, and they're in a very disturbed environment. But along Sanriku, all these black dots are observations of tsunami run-up, and along Honshu and along Hokkaido here. And, oops. The red is the prediction for the model that was obtained by some trial and error modeling to try and get a slip distribution that was consistent with the buoy data, both regional and remote, and to try and match the run-up. And it had been asserted by several papers that you could not get a model that would be consistent with the seismology and the geodetic data and the tsunami data for these massive run-ups here, which are 40 meters or so as the peak. In fact, we never got a 40 meter. We couldn't quite fit the 40 meter, but we did get 38 meters. And at that point, I'm pretty happy. It's extremely complicated because you're basically, the wave is running up a cliff and splashing up. And trying to emulate that with the few meter digital elevation models and the nonlinear breaking of the waves, the formation of bores into the canyons that tunnel up. It's impressive you can do as well as you can, but I think it's pretty successful now. And again, the tsunami modeling has really gotten advanced. So the model that emerges from that is very similar to the model that we had within a day or two of the earthquake from seismology. So I was kind of happy with that. We can fit the seismic data equally well, and basically we still need 50 to 60 meters of slip out near the trench. We need more to the north to give the big run-up along Sanriku. This stuff here overlaps the 1896 tsunami earthquake zone. So it did participate largely in the rupture in this 2011 event. Now, if you look, these two plots, E and F, are reconstructions of the initial tsunami sea surface perturbation from taking the tsunami and just tracking it back through the ocean, not solving for slip. And there's an excellent correspondence, I think, between the tsunami modeling, just kind of, this is really a smart thing to do. You just take the waves and you propagate them back. You can reconstruct how the sea surface had to be disturbed. And it looks a lot like the slip distribution, which will look like a lot like the seafloor deformation, which will produce something very similar to this sea surface displacement. And so those models are showing some extension out to the north through this 1896 rupture zone in both cases. These other models are models that invert seismic, geodetic, and sometimes tsunami data together, but they don't fit the run-up. And they will underpredict the run-up because while they may have a tendril of slip extending to the north almost to 40 degrees, it's not quite as much. This is 20 meters up here. And so I think that we gain something, or at least we demonstrate within the notion of existence that there is a slip model consistent with the seismic. I won't show the geodetics. It's not tuned to optimally fit the geodetic, but it's a very good fit in my opinion. And you can fit the complete suite of tsunami observations. Okay, so I think there's been tremendous progress, and many of you have made it and contributed to the development of these codes and the strategies of joint inversion, exploiting the complementary sensitivity. But the question of whether past ruptures slip to the trench is really critical to resolve because we have a lot of data about events prior to 2000. We don't have any significant GPS or tsunami deep water waveforms to work with. So I've been looking for some seismological method, and the one that we think holds the most promise is the idea that you could use the energy that is radiated from an earthquake that goes down as P wave or up as little pp bounces off the crust under the ocean, this green path, or transmits across that crust and bounces off the ocean surface. And these waves, as they go back down, some will transmit, some will bounce, and you can get reverberations. And if you generate this energy, which we call PWP, you can imagine that if you rupture to shallow depth, you're going to generate a lot in the shallowest or in the deepest part of the ocean. Whereas if you're rupturing down dip, these waves will mainly sample shallower water, though at some azimuths you could get some energy into the deep trench, but it won't be seen at all azimuths. So this is interesting because we have a lot of data, and we can calibrate this against the many earthquakes that have happened the past few decades where we have great global seismic networks. And these are just some of the earthquakes that we do not think ruptured to the trench. 2007 Sumatra, that was down dip of the Mentawai event. 2007 Pisco's near the coast. The Iquique earthquake in northern Chile, they did not. And if you look at their signals, what you find is a nice P wave, complicated pattern. These are complicated magnitude 8 earthquakes, but it's over after about 100 seconds, and then it's relatively quiet coda after that. It's just not much happening after 100 seconds until you get phases like big P, bouncing off the surface halfway between the source and station. And then you have strong arrivals. But you've got an interval here which is very quiet. And that tells you, well, the earthquake's over. It's not radiating anything. In this case, there is a coherent arrival, and it actually flips polarity. It's an early triggered aftershock. But not much else is going on in these signals after 100 seconds. If you look at Tohoku, which I would argue does rupture to the trench, unlike those three, and you filter into kind of a sensitive passband, around 10-second periods is where the water reverberation in 7-kilometer deep water will be particularly strong. And you do see, after the nominal 150-second rupture duration, very strong reverberations. Okay? And they're not at all azimuths. There is some non-uniformity of it. This is for Chile. You see it strongly in certain azimuths. You don't see that for the other events in the comparable test frequency band. So I think this gives us a probe that will tell whether or not the rupture is getting out to the trench and generating these strong echoing reverberations in the ocean. Now it's also questionable, well, is the earthquake rupture still going on? Is there something after 100 seconds or 150 seconds releasing from the source? And then you can test that by looking at the S waves, for which there are no water multiples. And you can confirm that the rupture is truly over and that these things are generated by the Green's function, and that Green's function involves water reverberations. I think it's very promising because we could do that for the old earthquakes, all the way back to WSSN and before. We could look at older earthquakes and evaluate whether some of the famous big earthquakes in the past managed to rupture the trench and address whether or not those regions are capable of having tsunami earthquakes or can only fail when driven by deeper slip, et cetera. One last attribute that I'll mention that's pretty novel is that we're looking at the distribution of earthquakes in the aftershock series sequence to evaluate whether or not that tells us anything about the distribution of faulting, particularly its subdip extent. This is a cartoon for the Iquique earthquake, the slip function from one of our models with aftershocks. Blue is foreshocks, red are aftershocks that are distributed on the megathrust. And what we do is we look at the region that slips a lot. This is the Nicaragua earthquake, this is Tohoku, this is the Iquique earthquake, and we look at the distribution of aftershocks to evaluate whether or not they differ when you rupture to the trench or not, because these are all events that do, and compile systematically, I don't know, my slide got a little bit messed up, the distribution of aftershocks, whether they're within the fault area or outside of it. And that's what's shown down here, is that the solid line indicates the edge of the rupture zone. If they're to the left of that, they're within the rupture zone. To the right of it, they're outside of it. And what you find is that for events that are rupturing shallow, this population, versus events that rupture just the deeper part of the megathrust, there's a huge difference in the aftershock distribution and focal mechanisms. If you rupture to shallow depth all the way to the trench, the events will have a lot of aftershocks that are on the lower part of this graph, these being intraplate, typically within the slab, sometimes in the upper plate, versus interplate. So the intraplate is mainly normal faulting activity induced. It can overlap the rupture zone, but it would be within the plate if it's down here. And we see that's very different than if you rupture deeper on the fault. So like Iquique, if you rupture deeper, it has, most of its aftershocks are clearly outside the rupture zone. It would be one of these, this is a composite of many different mechanisms, but it would have no intraplate activity, or not significant amounts. So we've seen real fundamental difference in the pattern of activity depending on if you rupture down dip, you get a fringing rim of interplate aftershocks surrounding it, sort of a classic asperity-like model of a slip patch with a crack edge that has a stress concentration, good events, but you don't activate the intraplate environment. If you rupture all the way to the trench, either as an isolated rupture like Mentawai that just ruptures the shallow part, or as a big rupture like Tohoku that starts deeper and makes it to the trench, you get very different distribution. You get many intraplate. These little magenta stars are aftershocks within the subducting plate. And they're not only in the outer rise, but all around the entire rupture. You are able to activate intraplate faulting. We believe that this reflects a kind of a relaxation of the stress regime. When you rupture to the trench, you're breaking to the surface. You're closer to a total stress drop event, as is thought to have likely occurred for Tohoku. In that situation, when you take away the total interplate stress, ambient stresses from plate bending, from plate deformation around the edges of the slip zone, the transfer of stress around activates far more diverse focal mechanism activity than you find when you have a rupture confined to the larger depth part of the rupture zone. So again, this is perhaps a surrogate by which we could evaluate whether a rupture has gone to the trench or not, is to look for its aftershocks. We already know that, like for the region that slipped to the trench in the 2010 Chile earthquake, if our model is correct, it activated outer rise activity up dip of where it broke to the trench. It did not activate that in the other parts of the same rupture that did not rupture to the trench. So this could be an additional tool by which we could evaluate the past ruptures to the trench of earthquakes for which we don't have this wonderful seismic, geodetic, and tsunami data. So to summarize, there's tremendous progress. It's quite extraordinary. The convergence of modeling capabilities for the seismic, geodetic, and tsunami data, along with the proliferation of observations of deployment of great networks in all those communities, is now allowing us to resolve this question to some extent, though, of course, we're dealing with a finite amount of time for which we've had data. Of the data since 1990, of the 120 so events, about 10% have involved slip extending to the trench, which is more than the classic textbooks, which would have said 0. But these events, because when you rupture the trench, you have such strong tsunami excitation, they become particularly deadly. And because they rupture slow, with long durations, the stealthiness of these earthquakes can be particularly difficult to contend with. You don't get the onshore warning of strong shaking. This was demonstrated by the Mentawai earthquake, by the Nicaragua earthquake, and other tsunami earthquakes. When you slip under very deep water, out near the trench, you get strong multiples in that deep water. And that's a real flag that you have strongly excited them. Now, it is possible that on some paths, wave energy will bounce around and get into the deep water, even if you had deeper slip. And we're trying to figure out by modeling techniques when that happens, what type of azimuthal patterns will be diagnostic of that situation. But in general, if you have really strong reverberations, you probably ruptured into deep water. And finally, the aftershock mechanisms are reflecting the change in stress during the main rupture, and that seems to indicate very strong shear stress reduction when you do break to the surface. So that can be accompanied by the enhanced slip that occurred for Tohoku at the surface, so this total stress drop, the flinging forward that enhance the tsunami excitation in that case. But it's another method by which we might be able to diagnose the existence of slip to very shallow depth from the historic record, which would be a valuable thing to be able to do. Okay, so once again, thank you for having me come and chat with you and to watch all the exciting science you're doing. I really appreciate coming to see UNAVCO's update. Thank you.
Thorne, so I didn't see a publication about PWP reverberation. That seems like a question. You can hear me?
I can repeat it. I heard it.
Oh, okay. So that PWP seems like it could be a really good real-time determinant. It also seems like it would really stick out like a really sore thumb if you did a Fourier transform of it as a really very bright singular frequency. And that would be probably just that. It should be really identifiable.
Well, indeed, I've not written a paper on it. Oh, okay. He's arguing that this PWP excitation, which you can see here, this strong ringing, that shouldn't be there if it didn't rupture to the trench. So you could perhaps quickly evaluate a recording. Here you just need a couple hundred seconds of record. So before big P comes in, and you could set up a quick measure of that and perhaps help to assess very rapidly within the time that you're doing a moment tensor or whatever, whether or not it's likely to slip into the trench. I think
Right. Basically evaluate the Fourier transform.
Yeah.
Basically identify a singular frequency which this thing is popping off.
Yeah, this is selected by the frequency. The frequency of this ringing is really controlled by the water depth. So you'll have water reverberations in 3 kilometer deep water, 1 kilometer deep water, but when it's this deep water 10-second pulse, that takes greater than 6 kilometers deep. So yes, you might be able to do either time domain or spectral domain quick analysis. So it could supplement other early assessments, but it may be one of the fastest things we could do to trust whether or not slip went to the trench. And that would be valuable for tsunami warning if it holds up. Now, the problem I'm not too sure about yet is that the 3-dimensionality may interfere, and there may be environments where you can get energy channeled into this reverberative interval that comes from deeper on the fault, but we are trying to model. This is actually making synthetics for this in 3D is something no seismologist has done. It's a very difficult problem. Okay. There are a lot of papers that have noticed PWP, but we haven't tried to use it as a tool. I'm trying to use it as a tool. Okay, thank you very much.
Thank you all, and good night.